If not, tell me anytime. Okay, so first, so randomized benchmarking is a tool to benchmark how well quantum computers are working. So, and it works in this kind of mindset that we model a quantum computer as a set consisting of an initial state, some gate set, and a POVM that is approximating the ideal version, which would be like implementing the zero state, then some ideal gate set, and the computational basis measurement. Right, and we can imagine more general settings where we maybe have more states to prepare and stuff like that, but this already covers a lot that we're interested in. So this is what I'll be considering for today. And the goal of benchmarking a computer is looking at this relation and kind of checking how well it works. And the reason why we want to do this is manifold. So first of all, we want to be able to trust the results of quantum computation. So if you're unsure on a quantum computer, it gives us numbers. We want to be able to trust it. Okay, sure, it's not such a good example, but because it's easy to verify classically, but there are other instances like simulating quantum systems and stuff like that, where it's not so easy to check that the result is actually correct once you get it. So it would be nice to have a tool that would benchmark this relation and build trust in such a computation. Then the second reason is that we want to design better quantum computers. So we want to have some feedback on the experimental level. So the experimentalist builds a quantum computer and it works somehow. Maybe it would be nice to have tools that would provide the experimentalists with some feedback on their work and maybe guide future development. And this is particularly challenging from a theorist perspective because we don't really like the experimentalists have their own tools, how they benchmark their devices. They can tune lasers very well, they can tune pulses very well, and so on. But the goal of this kind of approach is to work on the application level. So we look at what the computer actually does in the regime in which we're interested and benchmark it there. So maybe we look at how errors scale with system sizes. We look at how much crosstalk there is between qubits. We look at how much non-Markovianity there is, for example. So this ultimately would be the interesting bit where randomized benchmarking can really benefit the experimentalist. And the third part that is becoming increasingly relevant and will be relevant in the future is checking that we're below the threshold for error correction. So error correction requires precise enough gates and precise enough computations. And it would be nice to have a protocol that will tell us, yeah, good, we're below the threshold, now error correction will work, or that we're not. So these, I guess, like to me, are the three most important use cases. So first of all, it's trust results. Right? Then second is advise design. And then third, check EC threshold. Right? Okay. And randomized benchmarking is a subset of these methods. So there are many methods to do this kind of thing, and randomized benchmarking focuses on the particular task of checking the gate set. So we have the initial state, we have the final, we have the POVM, and then we have the gate set. So randomized benchmarking is the method to return a number like this. So it's some quality measure on the gate set. That's ultimately what we're interested in. And what would be also nice is if we could somehow understand what this metric is, what's the measure that we're using to actually benchmark the computer, because even like abstract measures that only tell us about like abstractly what the computer does are interesting because then we can compare devices and so on. But to actually really achieve these three goals that I outlined before, it's really important that this D is somehow interpretable, that we somehow know what it means and can tell us more about it. So then we have some requirements. On the RB scheme. Okay, so I'll be saying RB, that's randomized network. Okay. So first of all, we want RB to give us a measure D of quality of the gates that's sort of independent of the quality of the initial state and of the POVM. Right? So this is what RB people call span robustness also, other people in. Right? So we don't want to be sensitive to any errors in the state preparation and in the measurement. We're only interested in the computation, in the gate set. Right? And then the second one is what I already said. So D needs to be somehow useful. So the experimentalist doing the RB experiment and getting this D should be really excited about getting the D and really know what to do with it. Right. Okay, so when we want to get a number like this, there is a really useful object that we can use to do that, which is unitary representations of groups. And the reason for that is that groups are easy. So first of all, groups have inverses, which means that we can do a computation, then undo it, and check that we did nothing. And second of all, unitary representation of them are implementable on the quantum computer. So useful. Unitary reps of, and finite groups in particular. And it's for these two reasons. So we can implement them easily on the quantum computer and they have inverses. And this observation kind of leads to this core idea of the whole thing. So where did I put it? Maybe I put it. So the core idea is the following circuit. So yeah, it's a very simple idea. And it's something that I already said. So we have a bunch of, we have the initial state that we had previously. So that's the one that our computer can do. So it's the zero state. And then we apply a circuit consisting, space. So, thanks. Right, so we implement some unitaries from the unitary representation of some group, some finite group that we choose, and we implement a sequence of them. Good. Then, in the last step, we just undo it all. So we do U of G1 inverse all the way to Gm inverse. Right? So, and now, and then we measure in the computational basis. Yeah, so G are elements of our group, and U is their unitary representation, so it's a gate. So we can apply to our zero state, and we can apply a sequence from the group of length m, and then we can undo it in one go, because it's a group. So it has inverses, so it's easy to do this. And because it's a finite group, it's also easy to simulate this. And so this circuit does nothing. It takes the zero state, rotates it to the zero state, and then it measures, and we should get a zero. But of course, if we have errors in our implementation, this won't actually be the case, and we will be implementing some noisy versions of these things, and we will get the wrong answer here. So, okay, so what does that look like? So we expect, wait, I can only use this part, right? Or not?
Sure. You can.
Okay, actually, I can see the video, okay. Alright, so what happens if these are noisy? So if these are noisy, we expect that the probability of success, where success means measuring zeros in the end, goes like this. So the probability of success of implementing a length m sequence like that will be some constant times the product from 1 to m plus 1, let's say, of pi, where pi is the probability that there will be an error in the given layer. So this is like a motivation. So don't worry that this is just blah-blahing a bit, but this is just to motivate the whole thing and to illustrate the core idea. So the core idea is that the errors will kind of multiply in this way, and because we expect them to multiply in this way, yeah, well, that would be useful later on. But what's the problem with this? So it gives us some measure. Like we could just apply the sequence, just choose one, do it, and output this PSM, and that would be some measure of quality of the gates. But it's a very bad measure, and it's a bad measure for multiple reasons. First of all, or like bad in the sense that it doesn't really satisfy these things, because our initial state and measurement error, it just also propagates throughout the circuit, so the success probability is influenced by them. And it's also not really useful because it's very specific to this particular circuit. And why do we care about the circuit? Well, there's not really any reason, because it's a very silly circuit to implement. So yeah, that's not very good, but we can already use this to do something smarter. So to get a useful randomized benchmarking algorithm, that would give us D with that satisfies the requirements, we pick a measure new on the group G, and instead of doing one of these circuits, we average over all of these circuits. So what happens? Well, maybe end randomize.
Sorry, I have a question. So the gate set G we want to test has to be a unitary representation of a sum group.
So not necessarily, but that would be the ideal case. So this is an important point, and I will discuss it later. But for now, we don't really care about the relationship between the unitary representation and the gate set. I just assume that the gate set is the unitary representation, but that is a crucial point that is actually still like an active area of research, kind of, even though it's kind of been resolved. But the problem with this is that we would need to compile these gates, and that will be problematic, and I'll explain why later.
And is the gate set the generators of the group, or is it big or is it small?
So that really depends. And that depends on the particular IB scheme that you choose. And yeah, there are good choices, there are not so good choices, but it needs to generate the group. Yeah, it needs to generate the group for sure, but it doesn't necessarily need to contain like super large number of elements of the group.
Okay, so it's enough to generate.
Yeah. So we pick measure mu of D, and instead of getting the success probability, we get like the average success probability. So I'll call this F, and this is the number that we measure in the experiment, kind of. Okay, so we take the expectation value over So, right, so what I'm gonna write now is the ideal version of the thing. So we'll have the 0 POPM, and then we have the unitaries. Then we'll have the initial state, which I'll just label rho. Right? Yeah, so that's the success probability, and it's 1. And so the reason why I'm writing it like this is just not to confuse everyone once I use the vectorized notation. So this notation is not so great because we suddenly see the use. So for example, UGM is appearing twice, and yeah, that's not nice. So instead, usually in all of the randomized benchmarking literature, we go to the vectorized version and write it like this. So E, and then we have right. So what have I done now? So I took the row and I vectorized it to get this vectorized version. What that means is I take the columns and I just stack them on top of each other. And now each of these omegas is U G1 tensor U star G1. And yeah, that's the right thing. So instead of now having like GM twice, we have it just once, so it's nicer. And then I have the POVM corresponding to the success, which is measuring a 0 in this experiment. So is everyone clear with this notation? Because this is like one of the crucial things that, yeah, can be confusing. You know,
the measure is just one or over one number, like it's just IID or
so the measure is over the group, so it's for a single element, and you sample IID from it n times, and then based on that you get a vector in the end. Okay. And now the whole. Yeah. Yeah, exactly. The reason why I write it like this is because in the end, if when we implement it, I just gonna put tildes on everything, and then I just keep row tilde. But row is 0 for now. Yeah, this is 0 state for now, and it's a pure state.
So this is 1.
This is 1, exactly. This is 1. But the point is that we don't have perfect quantum computers. So now I put, yeah, well, yeah. Yeah, maybe what I'm gonna do is instead write like F ideal, this is 1, right? And then we'll have actual measured. And the hope is that this will have the following functional form. So it's gonna be an exponential decay guided by some real decay parameter P between 0 and 1. And then we'll have 2 other free parameters that contain all the errors in the state preparation and the measurement. And now this is the real one, so I put tildes above everything. And now, yeah, this is what we have. And so why should we even expect this? So the reason to expect this is sort of like morally this formula. So we expect the errors in the layers to kind of multiply, and yeah, and this is the point why this is dodgy and why there is still like 50 minutes of the lecture left. The reason for that is that you have correlation between the final element that you draw and the previous ones, because the final element that you take is the inverse of the previous one. It's not random at all. It's conditioned on the ones that you drew before. And therefore, this formula is not really right? Because we want to, we're averaging the error over each layer, but there is some error due to the last layer that's correlated with all the others. So that's why I still have 50 minutes. But the hope would be somehow show that at least approximately this somehow holds, and we can fit an exponential decay to it. And then our P will become our D. So that would be the performance measure that we output. And the extra hope would be that P is the average. Yeah. Okay, maybe I do it. Yeah, so the extra hope is that P is close to the average gate fidelity, which is the expectation value over nu of f of omega tilde and of g and omega of g. And here f is, it depends on where you look, because it's actually not really the case for all considered instances, but this f is either the entanglement fidelity or this average fidelity. So I can write the equation. So f is either this thing, trace, yeah, of psi, yeah, psi, and then psi. Or it's this entanglement fidelity. So we take the maximally entangled state, and then we do this channel. This requires that the phi is invertible. Omega, omega, and omega. Right. So these are the two choices that usually are made. And by the end of this lecture, I'll show that in a simple case of gate-independent errors, it's the second one. But yeah. Okay. So what's emerging here? So we want to get a useful measure for the distance of our implemented gate set compared to some ideal gate set that we want to implement, using this randomized procedure where we implement the identity circuit in a complicated way using length m+1 deep circuits drawn from some measure over some unitary representation of a group. And then we want to fit it to an exponential decay. And the reason why this is interesting, because for example, let's take a very simple example. So let's take the finite group to be the Clifford group, and let's take nu to be the uniform measure on this. Then this average is over super many this is massive average, right? The number of length m Clifford circuits is massive. So this is not very practical. So what we instead do is do this Monte Carlo estimation. So Fm is an average success probability, which means that it's a bounded variable. So that means that Monte Carlo is efficient for it. So we can just sample a bunch of those circuits and obtain an estimate f hat which is unbiased. And then we can just fit this, fit f hat to this form, and output b. Right. So that means that we got to a point where we do have some scheme that kind of claims to fulfill our requirements from the beginning.
If you want, you can also use this wish.
This one. Oh, this one. Yeah, that's very better.
It's already.
Yeah.
There's also a good chalk. Right next to it.
I'll check this. Okay, so are there any questions at this point?
Yeah, is it clear at this point that you don't get problems with like multiple decay channels? Or...
Yeah, so it's not clear at all,
Okay.
and it's also not true.
Okay. No, because you said the main problem with this is that you have correlations, and I thought like, okay, but if you average over different things with different probabilities, you also get like, multiple decay channels.
Yeah. So at this point, I like this statement is a belief.
Yeah.
And I haven't shown it at all, and it's actually also not true in general. And exactly, like if you do take representations that consist of more than the trivial representation, the trivial irrep and just one other irrep, then you won't have this, and you will have multiple decays.
In case, okay, in for many groups, it's known how to average, for example, for and this kind of stuff. For example, for assuming that you have a noiseless sleep for you can complex is average.
Yeah.
I mean,
Yeah, exactly. So that's what I'm gonna do just now.
Oh, okay, so
Yeah.
and as a spoiler, this formula, okay, for will be exact or
Yeah. So yeah, exactly. So as a spoiler for Clifford, for the uniform measure over Clifford's, this will be exact, and the exact in the case when we have gate independent errors. So if you have gate independent errors, then this will be exact, and P will be exactly the entanglement fidelity for the error channel.
assuming the noise that is independent each gate and possibly independent each gate.
No, the same.
Always the same.
So it's the stupidest, simplest case that is completely unrealistic. Yes.
And for the groups, instead it's not sure. Depends by number of the from the unit.
So
Yes.
So I think it is the best to answer this later. So first But the spoiler is that this is the case for approximately even for any finite groups and also for gate dependent noise. But what is not true is that P would be the average gate fidelity. Or it is true with caveats.
Could you repeat the argument why Monte Carlo sampling is good?
Yeah, so-
it's bounded? Or...
Yeah. So because F is a variable between 0 and 1,
Okay.
it's bounded, which means that also its variance is bounded,
Okay.
which means that just taking more and more samples, we will converge to the
The things.
and like, well, the reason why I say this, so for example, if F scaled with n, then for large numbers of qubits, we would not have any hope of doing it. So actually, like the hope of this whole field is to achieve a method that would actually have this like constant effort in the number of qubits. So and this is really important because as I mentioned, all those the experimental benchmarking methods that people actually use in the lab in designing quantum computers, those are usually not scalable and they don't have access to these many qubit regimes at all. So this is a regime where randomized benchmarking is actually interesting. That's like we do know about the individual gates a lot, but we don't know what happens if we then do a computation on 1,000 qubits. Then we don't know at all what happens.
I mean, the size of the group.
The size of the group does grow, and the classical post-processing involved in some of the methods, because some of the methods are not just sampling like that, will grow. Oh yeah, because you're talking about compiled gate elements, but yeah, in the end I will get to this, because at this point it doesn't look like it's going to be scalable, but it will be scalable. Like, you don't need to compile. Yeah, but never mind. This is kind of talking about something that I want to talk about later. So yeah, let's get back to basics. Okay. Okay, so what I'll do now is that I will look at the simplest case possible. Wait, is that true? No, there's one more thing. So first I wanted to summarize where we got to. So the protocol, yeah. So the protocol. Oh, that's a way to shock that. Okay, so we have a set of lengths, and for each length, we sample G1, GM from the probability distribution that we chose. And then we sample from the computational basis of the circuit UG1 inverse G M inverse M UG1 0 implemented on the quantum codes. Then we record 1 if we get all zeros. Zero otherwise. And then we repeat k times. And compute average at that of m. Right? And then we fit m hat of m equals a approximately a b to the m plus and return b. Well, in addition to that. Okay, so that's the product. And then this is like the most basic protocol, and there are some complications that are getting around caveats that I will be talking about later. But this is the basic idea, and this is also like what is usually done in labs, because most of these new things, they haven't really been implemented. Some have, some haven't, but yeah. It's like the randomized benchmarking landscape is very confusing, and there's a lot of different stuff, and it's not really like settled what will actually end up being the state of the art. But this is usually what is still done today with Cliffords and with the uniform distribution of it. Okay. So now we have the protocol here, and that means that we can obtain our first result. Yeah, at this point, yeah, I wanted to also like define groups and stuff, but I think that's not necessary, and it's just gonna confuse everyone. So I think that's just not so necessary. But yeah.
One stupid question. Previously we had some of these views where it's the acting on all qubits simultaneously.
Yeah.
So you say it's done in practice. Is it really that you can directly implement like a huge n unitary like
huge n qubits n equals 2, yes.
Okay.
Yeah. So you're pointing to
you want to compile it and then
yeah, exactly, yes. So that's why there are these other proposals, because yeah, but yeah, I'll get to this discussion after I go through this proof. But yeah, that's exactly the point. Yeah. It's not very practical for larger systems, but the hope of randomized benchmarking is that it should be applicable to large systems, and that's the interesting regime. Yeah. So yeah, now I'll just go through this. So consider G, the Clifford group, on n qubits, and consider nu. Okay. Then we take omega to be the conjugate action of the defining representation of this. So we just take the Cliffords as a matrix and we apply them. Apply to state rho will just be u of G, rho u of G. Right, so that's our representation. And then nu is the uniform. Uniform distribution on the Clifford group. And now we make a massive assumption that omega tilde of G is equal to some error channel phi times omega of G, right? For all of G. So this is a huge assumption. It's gate independent error, and it's completely like wild because we are implementing full Clifford elements, and we're saying that we can implement every full Clifford element with the same error channel. Insane. That's definitely not the case in practice. But let's just assume that's the case.
Times as in composed with.
Sorry?
Times as in composed with.
So I'm still writing this. Yeah, right. You're right. So actually, what I meant here was this, and then that's rho. Yeah. So I'm working in this like vectorized form. If you like pictures like me, then this is this. That's the representation that we're considering. And what that means, so here, when I say phi, I just imagine phi being here, and phi is a CDT. Yeah, no, but yeah, here's a bit of a mess, so eat it. Okay, so now, so this is a big assumption, and yeah, it's bad. But this is the reason why people look at randomized benchmarking. So I will go through the proof, because actually showing that this is a good idea in general, it's not so easy. Yeah. So what is our f of n now? Right, so we're sampling. Okay, yes. It's true that I should probably do this. And then I'm just gonna write E, but that's the E of success. So that's the POVM element considering connected to measuring 0 in the experiment. So that's what I have. Then I have omega tilde of G1 inverse inverse u of omega tilde of gm, omega tilde of g1, and then I have, right, so I'm still taking the vectorized form. Okay, now what's this? So now I do this, and I get phi here, then I get the noiseless version, and then I get phi here, and again the noiseless version. Right? Oh, there should be a tilde here. And what I do now is that I use the fact that we chose this beautiful uniform distribution over the Cliffords, which is also the Haar measure of Cliffords. And what the Haar measure means is that we can multiply each of the elements. It's a measure invariant under the group action. So we can apply a constant element to each of these G's, and it won't change anything in the expectation value. So the transformation that I will do is to transform G2 into G2 G1 inverse, then G3 into G3 G2 inverse, and so on. Right? So this transformation, what that does, when I look at this element, right? So I have G1 inverse times G2 inverse, right? So G1 inverse times G2 inverse. Under this transformation becomes just G2 inverse. And we can do this recursively. G2 inverse times G3 inverse will become just G3 inverse, and so on, until we get rid of all of these in the final term. So, right, so now let's just write it. Right, we'll have phi. Now in this inverted one, by doing the transformation, I get rid of all the G's except for the last one. So I'll only have GM inverse. Then I will have my error channel again. I'll have G omega of GM. Then I'll have omega of GM minus 1 inverse. Then I'll have my error channel, right? The reason why this is the case, because is that the case? Yeah, that should be. Yeah. Because we transformed GM into GM inverse. So that's why GM minus 1 inverse. So that's the one here. Yeah, I'll just include it here. GM into GM minus 1 first, right? And I then use the group property. So we would have omega of GM minus 1 inverse, but I can split them up because it's a representation of the group. Yeah, does that make sense to everyone?
What?
Yeah, so I do all these transformations, okay, and this one changes into this, and then I just split.
Yeah, okay.
And well, I just keep going, GM minus 1, right? And then all the way to omega G1 inverse by omega of G1. So yeah, sorry, that's visible though, right? So, and the point of it is that now I grouped all the G's together. So I have one term like this, then I have one term like this, and then I have one term like this, and the G's are completely split up. So I can just distribute this average over each of these things separately. And what is going to do this for? Yeah, so equals E tilde, and then we just have this phi tilde to the power of n, and then we have rho tilde. And what this phi tilde is, it's defined as this like twirl over the air chain. So it's G mu, and then we have U. Reverse by omega G, right? And I'm just gonna write it in pictures. Yeah, I think that's probably this. Okay, so that's what it is, right? Yeah, everyone can see why this is the case. No.
Yeah.
No. No.
But that is the first, fine.
Yeah, good point. Yeah. It just gets absorbed into this. Yeah, and the reason why this is fine, as I said in the beginning, we aim to have a measure that's independent of the state preparation and POVM errors, which means that I don't care, and it's just gonna get absorbed into the constants A and B. That's the upshot.
One small question: the assumptions. What exactly are the assumptions you take from the representation?
So at this point,
Faithful, I guess.
So at this point, I'm just considering the Clifford group, and it's like defining representation through the conjugate action.
But I was wondering if you have some special representation that has like a special role where it's extra really on, then it's good.
Yes.
Like,
yeah.
So there's some
So
reaction or something.
So what will happen then is that A will be 0 in that case, in here, in our fitting model, and we won't really be able to fit anything. Yeah, that's an important point. Yeah, the point here is that the twirl over an error, over a CPTP map, over the Clifford group, which is a 2 design. I'll explain this later, but this is the depolarizing channel, and the depolarizing channel has a fixed point of the maximum mixed state. So if I use rho as a maximum mixed state, I won't get any signal. And that's a limitation of the method. Like if you have super noisy initial states, you will get small overlaps, and yeah, everything is screwed. Okay, so we're here. Because I like pictures, I don't like this, and I prefer to work with the vectorized representation of this. And this looks like this. So I have U dagger of G, then I have U transpose of G, and then I have again U transpose of G, and then I have U dagger of G, right? And then I have my phi. Oh, well, okay. Yeah. So what I did here is that I had my phi at the beginning, and my phi was a CPTP map, so it mapped right. Phi acts on rho like this, and I can just take these 2 legs and bend them over here, and this is what I get. That's back phi, and then I can apply my representation on it. And I just like decompose my omega into the different U's, and this is what I have. Oh, and look at that. So maybe people will be familiar with this object because that's the moment operator of this measure of the probability distribution. Yeah.
What's this moment, but then for second moment?
Yeah. So this appears over these like randomized protocols and stuff. And why it's useful is because it can be easily evaluated for many cases. So in particular, there is something called the two design property. Okay. So we have, yeah. Oh. Okay, two designs. So the theory of two design is concerned exactly with study of these objects. And a two design is a probability distribution over the unitary group. Yeah. And okay. And this is new. And the property of this new that makes it a two design is that the expectation value of this kind of thing is the same as the expectation value over the R measure over the unitary group of the same thing. Yeah. So the R measure is the only the unique invariant measure over this group, the unitary group, and we can form this object for such group, and then we can measure, then we can compute the same object over this other distribution, and we can compare these two things. If they're the same, then we say that nu is a true design. If not, then it's not. Yeah. And there are some smart ways of computing this object. And if you don't know about those ways, you can just look into Antonio's tutorial and just find the formula there. It's called Van-Gouten calculus, and yeah, you get this. Yeah, like that. Right. Minus 1e. And then you get this thing. And then you get this thing. And then you get this thing. Right. Yeah. So yeah, I don't know. I don't think it's very useful to derive it here. You can just find it in textbooks and in Antonio's review, and that's it. Yeah.
This, because you just said it's not really about this calculus, but it's only for second moment.
Yes.
Of second moment, it's problem.
Yeah. The point is that this is always, so this is a projector that's quite easy to show. So you can take the dagger, and then because mu is symmetric on the inverses, you can just invert everything and it's the same thing. And then you can just take the square, and because it's invariant, you can just multiply and you get the same thing. So it's a projector, and the rank of the projector is the yes, is the number of irreducible representations of this representation.
The number or the multiplicity of the
The sum of the multiplicities. Right? I'm suspicious. I hope I'm not saying something. So I think that's.
I thought it was only projecting up to the trivial.
It's the cognitive of.
Yeah.
Well, but in this way you can see it as like the trivial.
Right, so this is all the stuff that does not decay in the
yeah.
in the
think that.
But you have different cubes which all decay, they would still not contribute to publishing.
Yeah,
Just about the ones. The ones which contributed to that.
yeah.
Which I would call trivial.
Eventually, number.
I think.
But well, so the point is that this is a rank 2 projector now for the Clifford group and for this is a rank 2 projector. And the reason why it's a rank 2 projector is because it's projecting onto the subspace spanned by the identity and the flip, and that corresponds to the trivial array and to the non-trivial array because it's the conjugate action. Yeah. So by trivial array, I just mean the trace, the traceful part of rho, and the traceless part of rho is the other notation. Okay. Yeah. Well. Okay. Well. So yeah, we can just find this formula and that's it. Okay, but yeah. All right. So now a crucial piece of information. The Clifford group is a 3 design, which means that it's also a 2 design, which means that this property holds for it. So we can just take this formula and just stick it in here, and get everything out of it. And so now what we'll need is how these things act on my vectorized phi. And yeah, it's quite nice. So if you take phi and we apply this to it, then we get this kind of picture. And if we apply this to it, then we get this kind of picture. Right? And what is this? This is just taking the maximally mixed state, applying phi to it, and then take the trace times d.
You said maximally mixed.
Yeah. Well, so this is the vectorized version of the maximally mixed state. This is the identity matrix where it bends the like. But if you consider this as a pure state on a bipartite quantum state, then it would be maximally entangled state. But like in this picture, they're kind of the same thing. It's just a different interpretation. And we have just one system, so it's the maximum mixed state. Yeah. And because the phi is trace preserving, so I take the identity, I run it through a trace preserving map, and I take the trace. So it's the trace of the identity, it's t dimension of the system. And then this, well, this actually is just d squared times the entanglement fidelity of phi. Okay, so that's quite crazy, but it's true. And the reason why it's true is the following. So I said, right, I defined, okay, so maybe we can have the definition of entanglement fidelity here again. So entanglement fidelity, is this omega, and then we have this psi inverse, tensor identity applied to omega, omega, and then omega, right? And when I say entanglement fidelity of just one thing, not 2 things, I just mean the other thing is the identity. So I just take this and do it with the identity. So that means that Fe of phi is omega by their identity applied to omega, omega, omega. And now in pictures. So we have phi, we have, so that does this. We have the identity, right? So that's this part. And then we're taking, and now it's the maximally entangled state, and we're connecting things. So we're connecting this here, this here, this here, this here, and we're missing, the dimension minus. Right, because this is normalized, so I need to write it like this over we have 4 with these. Does that make sense? Okay, so now we have nice pictures. We know what these 2 things apply to phi do, and we can write them out, write them down. And well, so now I just take this, I plug it into that, and what do I get? So I get that the vectorized version of phi tilde is 1 over d squared minus 1. And then I have this times d squared fe minus 1. And I have this times d times 1 minus f. Right? I just plug it in and put some terms together. So that means that I can write phi tilde in the not vectorized form. And now, so if I bend the legs of this like that, it's the identity. So that's d squared f e minus 1 over d squared minus 1. That's the identity. Plus d squared minus f over d squared minus 1. And now what's this? That's the projector onto the maximally mixed state. Aha! And that's the depolarizing channel. Yeah, so okay, let's maybe step back a bit. So what did we do? So we assumed that our errors are all gate independent, so we can write the omega tilde as a product of one error channel times the omega noiseless. And that allowed us to do this trick with relabeling the gate, the group elements in such a way that we can collect all the different G's together. And that allows us to write the whole thing as just one matrix to the power of n sandwiched between 2 vectors. And then because of this 2 design property, we can actually evaluate what this phi tilde is, because we can evaluate this moment operator. We can evaluate one of the averages, and because we decoupled all the G's from each other, it's just the exponential of it. Yeah, and how did we evaluate it? So we looked into Antonio's review, we got this formula, and then we noticed that applying these things to phi actually has physical meaning. In one case, it's easy to compute, it's d, and in the other case, it's it's a multiple of the entanglement fidelity of the channel. Yeah, and then it's just a bunch of algebra, and then we get here. And we get here by again bending the legs. Yeah, because so bending the legs here is this, that's the identity, and bending the legs here is this, and that's d times omega omega. And we get that. Okay. And so how does it relate to our protocol? So where are we? Here, and we computed this expectation value. So, okay, what happens now? So I'm gonna delete a bunch of things.
Yeah.
Mhm.
Yeah, for this you use the spine as unit.
No. So it's trace preserving. Because I just use that the identity applied to phi traced is trace d, because it's trace preserving. So the thing that came in was the identity with trace d. The thing that came out also is trace d. Yeah, what do I want to delete though?
And,
Uh-huh.
so you take here this average without, like you weight the terms with the same prefactor and you want for this FM. But so, and in this way you project the things that exactly commute. Yeah, so you get F12, you get commute, it's nice. So you can also design prefactors based on like the group characters that would project you onto a different era. So would project you onto states that have a well-defined commutation relation. So if you project onto one era, it will also be like they will not commute exactly, but up to a fixed phase or so.
Yeah.
Is there some use case for that in these benchmarking applications where you, because it's just like weighting them with different prefactors, you would not get like the same channel there out, but like is this also done?
Yeah.
Any interest or?
Yeah. So first of all, the problem is that if you're in this realm of gate independent errors, then I think that what you're saying is probably right, because we can really decouple all of the G's from each other, and then you could really design this and get and project onto different irreps. Because in general, if you have more irreps than these two, you won't get this nice one exponential decay. You will get a couple, and that is hard to work with because fitting multiple exponentials to one curve is difficult. So then it becomes like computationally challenging or numerically challenging, and you also need super high precision in the estimate. Yeah, so that would be really useful. But the problem is that this assumption is bad. So what instead is done, there's this framework of filtered RB that came out like 2 years ago that I think, and that does exactly this. So instead of, so it's a bit different. It doesn't have the inverse. Instead, it correlates the results of measuring in the computational basis of random circuits with some filter function that essentially performs you what you said. Yeah, there's more to it. I would have to take too much time to do it now. But
is this restricted to? Okay, so you have this big group G to the M, or same group but M times. Right, that's what you say. Like the expectation value is over.
Right. Okay. Yeah,
so,
sure.
So you have this big group, and this group has like loads of irreps, and there are some of them whose character functions are like products over individual. So, and for these, you could make this.
Okay, so that's slightly different than what I had in mind. Because yes, that's true. But the point is that you always want to put it into this format where you're actually averaging over each of the normal representations separately. So of this scheme, I had not heard that you would just take the whole thing to the end. Because I guess the problem would be that your irrep structure would change as you increase M.
Exactly.
And because you need to look at the function of M as F as a function of M, then I'm not sure what you.
I think you can't push the classical expectation value into the average channel.
Right. Yeah. Okay. Yeah.
But anyway, I was just curious if this is often used or not. So.
Yeah. So what is used is if I choose a more interesting representation that will have more irreps, I can project onto individual irreps. But what I mean by that, I really take just a single copy of it, not these M copies. Yeah. Okay. Yeah. Yes, this is. Okay, so we're not at exponential decay yet. So we need one more thing. And I think that probably delete this. Mm-hmm. 15 minutes, okay. Yeah. So what we now got is that phi tilde is the deporizing channel of strength Q, where Q is d squared as 1 minus the entanglement fidelity of the original error channel over d squared minus 1. Right? And now, because the data, yeah, I deleted that, but the data looks like this. Taking the power of the error channel, of the depricing channel, it just does this. Yeah, and the way to, yeah, maybe everyone knows this, but the way to see it is that the depricing channel kind of looks like this. So the depricing channel with strength Q in some basis looks like this, 1 minus Q by, and this is the basis in which this corresponds to the maximally mixed state, and this corresponds to this is the projector onto the traceless matrices, and yeah, that's what the depricing channel does. Because if you take, like, it does nothing to the trace full part, and it decreases the trace less part by a factor of 1 minus Q. Right? So that means that if so it's a projector with this kind of structure, and not projector, sorry, it's a matrix with this kind of structure. So that means that if I take the nth power of it, this one will just stay, and we just get the power of m here, which is why we get this. Oh, that's not true, right? Yeah, that's stupid. But yeah, okay, sorry, no. But so we have this representation, and that means that to the power of m, we get the following: we get 1 minus Q to the n times pi. Right? This is what we get, and we can just plug it into here. And we'll have E tilde pi tilde to the m rho tilde equals, and now we'll have one term that will correspond to this subspace, and that will be E tilde pi rho tilde, and then we'll have 1 minus Q to the m, and then we'll have another term that corresponds right. So I just took this form and I just applied it to this formula, because we have this, and this is exactly it, right? This is exactly a b to the m plus b, where a is E tilde by rho tilde, b is E tilde omega rho tilde, and b is 1 minus Q. Yeah, and that means that because Q is this, that means that we can invert this relation, and we can just compute the entanglement fidelity from measure. Yes. So now we finally got to the end. So it's assuming this really silly assumption that we have constant errors. This procedure actually gives us this form, and it gives us P that we can interpret in this way as the entanglement fidelity. So we can just plus versus cylinder. Okay, and given that I'm getting to the end, let's just meditate a bit on what we've done. So, and what are the problems of this? So first problem that's already been mentioned is there are some rows that that will kind of like commute with all the representative with the whole representation, and we won't see any decay. And those are, so for example, if rho tilde is the maximally mixed state, then its projector onto the traceless part is 0, and we just get A equals 0. And we have massive problems because then we can't fit anything. If it's close to the maximally mixed state, we get very small signals. So we probably need very accurate estimate of everything. So that means that we need to sample a lot of these random circuits, and we need to measure them many times. So big problems. And this is especially pressing if we want to go to large system sizes, because if we have a large system size, then states become close to the maximally mixed state, and yeah, problems occur more often. And maybe like the most problematic thing is that we're implementing full Clifford gates, and full Clifford gates require like n² deep circuits in general to implement. And that means that the error in a single Clifford gate will scale really badly with n. And that means that the signal will just decay very fast. And again, it's going to be difficult to estimate the decay parameter. So this scheme is not very practical at all. Like maybe even after one Clifford, we already are so close to the maximally mixed state that we already like lose all signal, and then we don't get anything useful out of it. So this scheme has problems, and this also leads to the biggest. Oh, yes, and this also leads to the biggest developments in RB in recent times, which was to. So instead of sampling from the uniform distribution of some group like the Clifford, maybe we can only sample from the generators of that group and only implement the generators and not the full elements. And it actually turns out that this is still kind of true, and we'll still kind of get exponential decays, and we can still get some interesting information out of it.
What's this
We
called?
always get exponential.
Well,
Way above it.
so you get exponential decays, but you may have exponential number of poles. Like in general, you will always get an equation like this, but this matrix will in general have exponential number of eigenvalues, and you will get exponential number of decay parameters, and then you can decide them. Sorry?
It will always look like exponential. Always fit it.
Well, like if you have a superposition of them, then it's difficult to fit it and get an accurate estimate of them.
I think it's difficult to find more than one value.
What do you mean? Like so in general, it's gonna look like this. We'll have just a sum over p of p to the n with some alpha p, and fitting this is not possible.
Well, but don't modify something exponential. Value can fit it.
But
Like
you
you
would,
find the alpha, say.
yeah, finding the alpha is hard, but even the dominant one, you would need to wait until all the others decay.
No, dominant one is the one that. Right. Oh. Yeah.
Like if all the p's are close to each other, then like what do? We would have to wait for super long circuits before you can actually fit one dominant decay.
No, but I can take the power meter.
The best fits it, right? Okay, yeah. You can always fit an exponential, but what will you do with it?
It's an interesting quantity and it's formalized.
It isn't. Yeah, you call it your number, but yeah, it doesn't mean anything. And well, first of all, under this assumption, it's not, because you get the entanglement fidelity of the channel.
That assumption.
Yeah, and then in more general cases, what happens? So if you consider gate dependent noise, if you consider gate dependent noise, what you instead get is a value that is the entanglement fidelity in a certain gauge. So okay, so when I'm getting into this discussion, okay. So at the beginning, I said that the quantum computer is a set of initial state, gate set, and POVM. And you could imagine, okay, so I'm just gonna say this. I have rho, I have a gate set, and I have a POVM. And I can imagine like inserting a matrix here. Okay, let's just consider the vectorized. A matrix here, and then a matrix here, and a matrix here. Like this. Right? And all experiments that I can do with this quantum computer will have exactly the same solutions as the previous one. And the problem is that the decay parameter is gauge invariant, because I don't care how I describe it, it always just does it and I can fit it. But entanglement fidelity is not gauge invariant. So it depends on which gauge I choose. And it can actually vary a lot. So yeah, so like you inherently cannot measure the entanglement fidelity using RB because it's a gauge. It's not a gauge invariant quantity, and the quantity that RB measures is gauge invariant. But the point is that there actually exists a gauge in which it is the entanglement fidelity, and you can always find it. It's like a natural gauge that you can choose. But then the problem is that this natural gauge sometimes leads to channels that are not CBD. So then it's not really a physical gauge. So this discussion is still going on, and it's still not clear what this number actually means.
Isn't the argument that the one number doesn't mean anything?
It's one way to resolve it. Yeah, you can be just like, let's just leave it, and we just get a number, and let's just call it a day. But I think that's kind of missing some of the potential advantages of doing benchmarking in the first place. So, for example, if you want to check that your computer is below the error correcting threshold, this would be useless because you just get a number and it doesn't mean anything in correction to the error correction threshold.
That's the argument. Not able to do that.
I think that's not clear yet. Like this protocol is not able to do it, but there are other protocols that look a bit different. They always like vary some of the key elements. Like for example, they don't implement the inverse, or they sample from just the relatives of the group. And there are more. So I wanted to kind of avoid this because I think the field is not yet at the stage where there would be like a standardized set of benchmarking methods that you would just take and apply. That's why most experimentalists still do this like kind of silly thing, like not very practical thing. So there's, for example, filtered RB. So filtered RB has been one of the major developments that allows for gate-dependent errors. It allows for sampling directly from the gate set, and it's actually fully scalable. Like the effort doesn't scale with system size almost at all. But it has some other problems. Like for example, you need a large number of samples. You need a large number of different sequences to get a reasonable number.
Is this N?
Yeah.
This still enters the scaling. Is that correct?
Which one you mean?
The kind of the number of layers.
This one?
Yeah, or like I was thinking of how if you include you have a phi dependent on which we use, then we still have like M different ones.
Oh, if you have like if you have time.
Yeah, but it's getting with the depth, right? Even though it doesn't go with the space size, it's still.
So you mean that you would have a different phi in each layer? That's your question.
Yeah.
So if you have a different phi in each layer, then you won't get an exponential decay. You will get a product of p's.
But why is including gate dependent phi not the same as saying phi?
Because yeah.
But every gate depends also layer.
No, not necessarily.
Layer independent. Layer dependent, but gate independent. Why you put that layer and gate dependent?
Okay, so if I had more time, I would go into these gate dependent things, and there is this idea. How much time do you have? Okay, 3 minutes. Okay, so I can say that. So. Okay, so there's this idea of an implementation map, and implementation map is a map from the group to CPTP maps, right? So I take an element of the group, and then I implement it on the quantum computer as a channel. And this is a model for gate dependent noise, because that means that depending on which group element I take, I have a different CPTP map, and there is no need to decompose it in this way as we had before with the gate independent one. But it is not like time. It is still time independent. Like if I take an element G and I apply it in the first layer, it will have the same CPTP map as if I apply it in the 100th one. So I could also imagine having a time dependent implementation map, and that would also have like layer index here.
Yeah. There's some conditions. So I have this omega, so the image of omega under G and image of omega under H. I compose them. This doesn't need to be somehow close.
No.
Not because the H is really independent, so it's not close to representation or.
Right. So if you want to get exponential decay out of it, you need to be somewhat close. Like if you just, for example, if this was like, if this was like completely wrong, like you have no hope of. You're right.
Yeah. So if the noise is slow enough, you still think that in some norm it's close and then.
Yeah, there's no condition on like it being close to a representation.
Yeah.
It needs to be close, like the implementation itself. Like we need something like the. Okay, well, I wasn't doing integrals, so it's not them now. So this kind of quantity. And yeah, here I guess you take the main one, right? This kind of quantity has to be small.
With the precise statement is written in this model or benchmark.
Yeah. Yeah. Yeah, because so the point with these gate dependent ones is that there's this like Fourier operator, and this is essentially the center of all the theories, but I don't have time to get into it now. I can do another one and explain that, but yeah, no, there's not.
And here you get like 2 decay channels, and you basically ignore one. Right?
Yeah. Yeah, but okay. Well, one more maybe. So if I take this, I just say the result. So the result is that if this is small, then I still do get exponential decay. I may get multiple exponential decays if I take a representation that has many reps. But if I don't, then I just really get this. And the assumptions that are still here are that the noise is Markovian because there's no memory. Like I always implement the same CPTP map, and it's not dependent on what I did before. So it's Markovian, and it's also time independent because it's invariant as we said before. And these are the most general conditions that have been for now implemented into RB. So this is like this is the standard. This is the standard setting where you want your new RB scheme to work, to be considered state of the art, I guess.
I mean, you still just get like always get it. So
What do you mean always?
like if you look at if you measure, you have your system, you do some gates, you undo the gates, you see how it decays inside. It will always be an exponential.
So it can be an exponential number of exponential decays.
Which looks exactly indistinguishable from
Not really. Like it can like you can get like this, right? Or you could get some oscillatory terms, for example.
What?
You can also get complex decays.
Oscillating would be unlikely.
What do you mean unlikely?
Never seen it.
Like you do something, you make an error, the likelihood of you undoing that error is small.
Oh, okay. Well, yeah, I don't think that's so clear how to relate it to this picture, because this picture does. Like if you have polystochastic errors, for example, then you can really like track these Paulis through your circuit, and then this argument I think holds, and then you wouldn't get these oscillatory terms.
Yeah.
But if that's not the case, I don't know. Yeah, I think this like there is more to it than just undoing errors to get this. There can be some like resonance with the length of the circuit.
I mean, I think the big problem probably that they have the exponential decay of the quantities from the end.
So that's one of the problems, but you can also have many exponential decays of similar size. So either you wait for a super long time, and then it's just impractical because you already lost your signal, or you have to fit your many exponentials, and that's just numerically not really.
What's the goal of trying to differentiate?
Because each of the decay parameters has a different, like you could, but
Maybe less cynical viewpoint of this is you just use it as a number, and then you use the same protocol over time, and as these numbers improve, you are confident that what you're doing in your experiments, moving the devices, and maybe they don't mean anything in these models where they do mean something. This one is really unrealistic, but it motivates it.
Yeah, but I think like it really comes back to the goals that I outlined at the beginning. Like you want to somehow like either check that you build threshold, or somehow inform the experiment. Tell the experimenters, oh, you have crazy amount of crosstalk on this device, or there's so much non-Markovianity that things don't work, or things like that. And if you give them these statements, they can use them because then they can like verify. They can look at their assumptions and see, oh, this is where it's going on and going wrong, and change the experimental design. Right, or you can predict how accurate the results of your computation will be. But if you really give up on any interpretation of the parameter, then like it's not so much better than just looking at one single instance of this and not averaging over the group at all. And like you also get a number.
Basically, that no reason was written better.
But there isn't. Like there are ways to interpret these numbers. Like it's still not finished, like it's still an ongoing debate kind of, but there is a way to interpret it. Like there's, for example, this direct RB, which is another like kind of state-of-the-art method. And this direct RB claims that it is actually close to the fidelity under some assumptions.
Okay, I think I will end it here. Thanks, Jonáš, for